In the previous video, we discussed the case of one observer looking at two objects separated by a constant distance. As the objects were moved farther from the observer, we eventually lost our ability to resolve them. In this video, we will consider the case of two observers, or one observer moving between two positions, looking at one or more objects. We see that for a single object, we have a situation very similar to what we have seen before, a triangle from which we can calculate angles based on the distance between the two observers and the distance between the observers and the object. In this graphic, we see two observers at positions A and B, looking at three objects located at different distances from the observers. As expected, the angle made by the two rays going from an object to each observer gets smaller as the object gets farther from the observers. If we go far enough, this angle becomes almost zero and the two lines would be almost parallel. This angle may be calculated and we can use the same plot as in the previous chapter, this time to represent the ratio of the distance from the observers over the distance between the two observers. Note, however, that the parallax of an object is normally reported as the angle shown in color, which is half the angle that we used in our graphic to represent angular resolution. Let us now focus on the view each observer has of the three objects. We show here how this view changes as we move from position A to position B. At position A, the green and blue spheres appear to the left of the orange sphere, whereas at position B, they appear to the right. At a position midway between A and B, the green and blue spheres are not even visible, as they are behind the orange sphere. Relative to the blue sphere in the background, the orange sphere, which is closest to the observer, appears to move a significant distance in the opposite direction to that of the observer. This apparent movement is more important than the apparent movement of the green sphere, located farther than the orange sphere. This relative apparent movement of objects in the field of view when the observer moves is the so-called parallax effect. Stars visible in the sky may be located at various distances from Earth. Most stars visible to the naked eyes are within 1,000 light-years from our planet, but many stars are millions of light-years away. We need to ask ourselves if the parallax effect may cause two observers on Earth to have a different view of the arrangement of stars in the sky. The farther apart two observers can be on Earth is equal to the diameter of the planet, that is 12,742 kilometers. When the parallax of an object is computed with this particular distance between the two observers, it is referred to as the diurnal parallax of the object. Objects closest to the observers are the most affected by the apparent movement related to the parallax effect. The closest star to Earth, besides the Sun, is Proxima Centauri, located 4.22 light-years away from Earth, that is 3.99 times 10 to the 13 kilometers. The ratio of these two values is huge, 3.13 times 10 to the 9. This is several orders of magnitude greater than the 5 or 6 thousandths delimiting the angular resolution of the human eye. We have to move much farther right in our graphic to find such a ratio. For this ratio, we find an angle of 0.0000000018 degree. This angle is even smaller than the angular resolution of the Hubble telescope. The diurnal parallax of Proxima Centauri is half this angle, 0.0000000009 degree. This is negligible. The lines of view from any two positions on Earth are practically parallel. Any two observers will have the same view of the arrangement of stars in the sky. Parallax may be used to measure the relative distances of objects, but stars are so far from Earth that diurnal parallax is not useful for this purpose. However, diurnal parallax may be used for objects that are closer, such as the Sun, or planets in the solar system. For the Sun, the ratio of distances is 11,731. This ratio is about twice the value corresponding to the angular resolution of the human eye. This corresponds to an angle of 0.0048 degree, well within the range of measurable values on Earth, given the appropriate instrumentation. The diurnal parallax of the Sun is 0.0024 degree, or 8.79 arcseconds. For stars, it is more convenient to use a greater distance between observers. A way to achieve this is to make two observations at 6-month interval, when the Earth has completed half its revolution around the Sun. Since the distance Earth-Sun is defined as 1 astronomical unit, the distance between observers AB becomes 2 astronomical units. 1 astronomical unit is 149,597,870 kilometers. The parallax of an object calculated this way is called the stellar parallax. In the case of Proxima Centauri, the ratio of distances is 133,448. This corresponds to an angle of 0.00043 degree, which is well within the range of observation with a telescope. With this method, a different arrangement of stars may be observed between stars that are closer to Earth and stars that are farther away. The stellar parallax of Proxima Centauri is 0.000215 or 0.77 arcsecond. When the stellar parallax of a star is 1 arcsecond, the star is said to be at a distance of 1 parsec.